In this video, we are going to study binomial distribution. Consider the following experiment. N independent coin tosses, where n is greater or equal than 1, independent coin tosses, with the probability of coin landing on heads being equal to p. Now, our goal here is going to be to calculate the probability of obtaining k heads in our n tosses. Let's slowly work our way towards the solution of that problem by starting at taking a look at the following particular sequence. Let's find the probability of obtaining the following sequence of tosses. So number of tosses here, n is equal to 6. And the number of heads we obtain in that sequence is equal to 4. Since we mentioned that our n tosses are independent, we can work with multiplication of probabilities. So the probability that our coin lands on heads on the first toss is then equal to p multiplied by the probability that our coin lands on tails on a second toss, which is equal to 1 minus p. So probability of our coin landing on tails is then equal to 1 minus p. Multiplied by probability that our coin lands on tails on a third toss, 1 minus p. Multiplied by probability coin landing on heads on fourth toss, multiplied by p, and so on. So probability of that particular sequence is then equal to p to the power of 4 multiplied by 1 minus p to the power of 2. Now let's try to generalize our problem and let's try to find probability of some particular sequence. By following the derivations of our specific example over here. Now, a probability of that particular sequence is then going to be equal p to the power of number of heads to the power of number of heads in our sequence. Since when each time we have heads appearing in our sequence here, that heads is going to contribute a factor of p multiplied by 1 minus p, which is the probability of tails, to the power of number of tails. So each time when we have tails appearing in our sequence here, it is going to contribute a factor of 1 minus p. Now let's go further and let's try to find the probability of particular sequence when we have k heads in it. So we're looking for probability of k-headed particular sequence. So it is going to be equal to p to the power number of heads. We have k heads, so p to the power of k multiplied by 1 minus p to the power of number of tails. Number of tails can be derived by 1 minus k, where n is the total number of our independent trials. Now we are ready to approach our problem of finding probability of k heads occurring in n independent trials. So probability of obtaining k heads is equal to, now the number of sequences where we have k heads is very many. Probability of each particular k-headed sequence is equal to p to the power of k, where k is the number of heads, multiplied by 1 minus p n minus k, multiplied by the total number of such k-headed sequences. So multiplied by number of k-headed sequences. Now we can use that derivation here by the following reason, that each particular k-headed sequence, they all have the same probability of p to the power of k multiplied by 1 minus p to the power of n minus k. Now, to find the number of k-headed sequences, we might consider it as the following problem. So we have ordered sequence of length n. And we are choosing k places for our heads to appear in that sequence. So we have k heads. And we are choosing places for our heads in that sequence of length n. Now, according to our combinatorics video posted previously, we know that the number of ways to choose k places for our heads in sequence of length n is given by n choose k. N choose k coefficient is also known as binomial coefficient. So the number of k-headed sequences is equal to n choose k, which brings us to the following formula: n choose k multiplied by p to the power of k, 1 minus p to the power of n minus k. Now let's take a look at a particular sequence. Let's say a sequence of a type heads, heads, tails, tails. And let's count the number of heads. Number of heads here is equal to k is equal to 2. Now let's introduce a random variable that is going to count the number of heads in our sequence. Let's call it big X. So big X is a discrete random variable which is used to calculate the number of heads. Now let's take a look at PMF, probability mass function, of that random variable X. So probability that our random variable X is equal to, so let me replace that small x with k. So the probability is that random variable X is equal to k, or probability is that we have k heads in our sequence of n independent trials, is calculated using that formula over here that we have derived before. N choose k multiplied by p to the power of k multiplied by 1 minus p to the power of n minus k. Now, we were looking at this problem as a problem of n independent coin tosses. We can generalize further and call our probability of getting heads as a probability of success in our experiment, which was equal to p. Then probability of tails, or probability of a failure on a particular trial is equal to 1 minus p, or if we give it a new name, let's call it small q. And we have n independent trials with the probability of success on a particular trial is equal to p, and probability of failure is equal to q, which brings us to the following definition of a binomial distribution. So distribution of number of successes in n statistically independent trials, where the probability of success on each trial is given by p and probability of failure by q, is known as binomial distribution and has the following probability mass function that we've derived just now.